This is section 3.9, derivatives of logs and exponentials. So a few notes before we get started here. So you have to know E is just a constant. It's approximately 2.714. And so E and pi, you got to realize they're just numbers. They just have a special name, and they're called E and pi. So, excuse me, just realize that they're just numbers. And we have a log function with a base b. And when you have a base e, that's known as the natural log. So when you see ln x, it's a log, and all the properties of logs apply to that. The next thing we have here is if you have a base 10, that's called a common log. And so on your calculator where you see log, that is base 10. And an exponential function is a constant to the x power. And so you already know this exponential function, e to the x, is where a constant is that special number that's about that. And so a lot of the derivatives, so we're going to learn the derivative of the exponential function and the log function today. And it's going to be highly related to the ln. You already know the derivative of e to the x. I am my own grandpa, so that'll make things easier. Now, you need to know these properties here. If you don't, these are things that could be quizzed on, but you just have to know them. You can get a copy of this from the Google Classroom page. I'll have a copy of these notes there. You can make flashcards, but these are properties that you will use throughout the year, and they're just assumed that you know them. The graph of e to the x and ln of x are given here, and I just want to point out a few things. It goes through the point 0, 1, and you'll notice the ln goes to the point 1, 0. Now that fact is important, and you will see we'll deal with some other things about ln's and e to the x's. And this is such a common function used in calculus, you just have to get very familiar with it. Okay, another thing you need to know, e to the x and ln of x are inverses of each other. They undo each other. Just like adding 5, subtracting. Adding and subtracting are inverses. Squaring and square rooting. You square something, then you square root, they cancel each other out. And so I have a few examples for you here. You have the e to the x function and the ln function. The e and ln undo each other, and that's going to be x. Same thing, it's just the opposite. We're plugging the e to the x into the ln. They are going to undo each other, and you get x. Now here is a little trickier. You need to rewrite this. Now we have the power rule for logs used very commonly. If you have a number in front of a log, you can make it into an exponent, p. I call this p'ing in front of the log, because if you have an exponent p, you can put it in front of the log. So that's one of the rules, and we're going to be using that here. So that 3 can be moved to be an exponent on the x. So that could be rewritten as e to the ln of x cubed. So that 3 can move in front or can stay on top. We chose to move it on top. Now we see the inverse functions cancel, and so now we can simplify this to x cubed. The next example, e and ln are going to cancel out here. So you have ln of e to a power, those cancel, and you will simply get 4x minus 1. We will keep on going here. This is quite simple. E and ln cancel, 3. And you'll see the same thing here, e and ln cancel, and 4. So that's an important concept you need to know. All right, here are your new derivatives that you have to know. Flashcard, memorize. These can be on the quiz tomorrow, so be prepared for this. So ln of x, the derivative of ln of x is 1 over x. That's pretty easy. And even if you have the absolute value on x, it's still 1 over x. So both of those you should know. You know this, I am my own grandpa. Okay, so we have that. Now here, log and natural log are related. The only difference in the natural log, the base here, is going to be e. So since you know the derivative of ln x is 1 over x, log, it's still 1 over x. The only difference is on the bottom, you need ln of your base. And think about this. Let me shrink this down a bit for you. So if on this one here you were to put ln of e, well, that's e to the first. That cancels. That's just 1. So really, there is a ln of the base on the bottom for ln of x. It's just not there because it cancels out. So highly related, ln 1 over x. We have log, it's still 1 over x. The only difference is, whoops, that's not supposed to happen. You still have 1 over x. You need ln of the base on the bottom. And you can kind of think of that b is on the bottom, so it kind of connects that way. All right, so I am my own grandpa. E to the x is e to the x. Now if you look at this, this is the same thing. It's just a different number to the x. This was 2.714 something to the x. This is some base to the x. So I still am my own grandpa, but I need to multiply by ln of b. So both the log has an ln of b extra, the log base b, and the exponent base b has an ln of b. You just have to remember with the exponential, it's on top with its own grandpa. On the log, it's on the bottom with the x. So I think that could be easy to remember. Wherever the x is, your ln is there. Wherever the x is, it's kind of on top. There's your ln of b. So those are 4 new derivatives that you have to know. So basically this chapter is working with new derivatives. All the rules of product rule, quotient rule, chain rule will all apply. And we're just going to be building on our vocabulary list or our derivative list. So let's do a bunch of examples. And we'll start with this one. We need to use chain rule. There's ln of box. So what's the derivative of y with respect to x? Well, we learned, this is a new one, it's 1 over x, but now it's going to be 1 over box. So the derivative is 1 over box, and we have to multiply by the derivative of box. What's the derivative of 4x? It's 4. Those 4's will cancel, and we get an answer of 1 over x. So that is our first example. For this next one, you should notice it's a product rule. You have to multiply those two. So the derivative of y with respect to x, we leave the first alone. We take the derivative of the second. Well, the derivative ln of x, we learned, is 1 over x. So with our new derivative, we pop that there. Plus, we leave the second alone and take the derivative first, which is 1. And those cancel, and we get 1 plus ln of x. We are on a roll. Let's just keep going. So really this section's pretty easy. You just have 4 new derivatives. You're applying all the rules that you've done before. So we have ln of box. Well, how do we do that? The derivative of y with respect to x. So ln, it's 1 over x. So in this case, it's going to be 1 over box. My box is supposed to be red. So box is secant x. So it's 1 over box times the derivative of box. But what's the derivative of secant? You should all know that is secant x tan x. The secants cancel, and it simply comes out to be tan x. All right, hopefully these aren't difficult. It's just all the rules you've learned before applied to new situation. All right, this is a straight up new rule, dy dx. I am my own grandpa, but since my base is not e, I need to multiply by ln of the base. There's my answer. That's just that new rule. I am my own grandpa times the ln of the base. How about this one, dy dx? I pull down the constant times, and what do I have? I have a base b to a power of a function. This is the new rule. I am my own grandpa times the ln of the base. So we can try this. I am my own grandpa ln of the base, but this was 2 to the box. So we had something different. It wasn't 2 to the x, it was 2 to the box. And I used the wrong variable. It's t, not x. Watch out. My apologies. So the derivative of 2 to the box, I am my own grandpa, is 2 to the box, ln of the base times derivative of box. So I need the derivative of box, which is 1 over 12. So if I multiply 108 times 1 over 12, that gets me 9, I believe. And then I have an ln of 2 and a 2t over 12. All right, so that is that one. We're just going to keep going. Now, at any time from now on, you could have even done it before, pause, try the next one on your own, see how you do, and then play the video and compare to my answer. All right, let me create some space here. All right, try this one and come back and I'll explain to you what this is. All right, this is an example of the power rule. That's x raised to a number. Remember, pi is just a number. So how do you find the derivative of that? You bring the number in front and you decrease the exponent by 1. So that, trickily, is pi x to the pi minus 1. So that is not an exponential function. So be careful, there's a difference. This is x to a number. This is a number to x. So you need to distinguish between those two. All right, try this one and come back and see what the answer is. All right, hopefully you did it right. This is a number raised to x. That's going to be this, a number raised to the x. I am my own grandpa times the ln of the base. Let's do this. I am my own grandpa times the ln of the base. Done. That's it. All right, let's just keep going. You can try this one, pause, and then come back. Okay, here we go. Realize that is a number, e, 2.71 something. You have box raised to a power. So what's the derivative of box raised to a number? Well, we bring that number in front and decrease that number by 1. So we're going to have e box to the e minus 1, but chain rule says we have to multiply by the derivative of box. What is the derivative of the inside? It's just 2x. And let me rearrange this. So we're going to have 2xe times x squared plus 4 to the e minus 1 power. And that is that one. We're just going to keep going. Try to stop this machine. You can't. All right. Next one. Go ahead and pause and try it. Okay. I was mean. I shouldn't have told you to pause and try this. This one's hard. You are trying to find dy dx, but here is the issue. This is nothing like any of the ones you've seen before, because here's the difference. That's not a constant, that's a variable. That's another variable up there. It's a variable raised to a variable. You don't have that. You've had a constant raised to a variable and a variable raised to a constant, but not a, okay. So here's the trick. You need to rewrite this. This is like tricky trick. So this is e to the ln of x raised to the power of sine of x. What is going on? Okay, this is like upper level big brain situation. Remember e and x, e and ln cancel. Those are inverse, they cancel, leaving you that. So that's why they're equivalent. Now we're going to do something else here. Next big brain step. So we learned we can p in front of the log. If we have an exponent p, we can bring it in front of the log. See? We are going to use that rule, and this is our p. This is an exponent right here. We're going to bring that in front of the log. So that's going to get us e sine x ln x. Now, this is crazy. Some of your brains are like exploding. Some of you are thinking, who in the world would ever think this? A lot of things might be going through your brain right now, but that is the big brain secret of this problem. Now it's e to the box. How do you take the derivative of e to the box? I am my own grandpa. It is e to the box. And I will put a box here times the derivative of box. So we need the derivative of the box here. Well, this gets crazy. It's a product. We have two things being multiplied. So we leave the first alone and take the derivative of the second, plus we take the derivative of the first and we leave the second alone. Wow. So, are you ready for this? This first part, I'm going to go backwards now. I'm going to use a p in front of the log rule and rewrite it as ln of x raised to the sine x. Then we're going to cancel e and ln, and we end up with x to the sine x, and we bring this down, and so we're going to have sine x over x plus cos x ln of x. And at this point, your brain literally pops and you can't think anymore. But you will never see a problem like that on an AP test, but that is just beautiful. Just the beauty of math and the things that you can do with your properties and just the little tricks. Some of you might appreciate that and realize, wow, that's pretty cool. Hopefully, some of you will. Let's just keep going. We're almost done. 3 more problems. All right, the next one, I wrote this wrong. I'm going to fix this. So let me get some white and get rid of that and fix it to what it's supposed to be. Uh-oh, I can't remember what was there. I can't remember. I got to erase that. And then, okay, 2x plus 1, 2x plus 1, 2x plus 1, 2x plus 1, 2x plus 1. So it's a big 2x plus 1. So what we have here is log of box. It's a base 5. The derivative of a log base 5, it's going to be 1 over box, just like ln x is 1 over x. It's 1 over box, but you also on the bottom need a ln of the base. So it's 1 over box, ln of the base, times the derivative of box. And the derivative of box will be 2. And so that's our answer. 2 is on top. And on the bottom we have ln of 5 times 2x plus 1. So that will be that one. And let's just keep going. Keep going. Let me erase and do that. Okay, we are trying to find dy dx. What you should see, we have a product. Two things are being multiplied. So we leave the first alone, and the derivative of log base 2 of n is going to be 1 over n, and also on the bottom, ln of your base. That's just the log, derivative of a log that you learned, plus we take the derivative first, which is 1. Oh, I forgot to say our variable's n. It's dn. Okay, so leave the first alone, the derivative the second. That's just the new rule you learned. It's 1 over n times, on the bottom you have an ln of the base. And then you take the derivative first, which is 1, because n is our variable, and we leave the second alone. And wonderfully, these n's cancel. So we get 1 over ln of 2 plus log base 2 of n. Now, there's another property we could use to make cool things happen. Let's look at this one here, the base change. I can rewrite this as the log of x over the log of a, log of x over log of a, but I can choose any base I want. So I can change it to base e, which is ln. Check this out. This is another beautiful thing. So this becomes ln of n over ln of 2. So any log, you can write it as the log of the top, n, over the log of the bottom. And any log you want, any base you want, and I choose ln. But now we have a common denominator. So we have 1 plus ln of n. Now, if you got this far, that is awesome. That is beautiful. I'm happy. If you get this far, that's like big brain level. Okay, most average person would not do that, but you should understand what just happened and why I'm allowed to do that. All right. This, you might want to take a break before you watch this one. Man, this is a nightmare problem because you would have to do quotient rule, low d high minus high d low over low squared. But when you did the derivative at the top, it's a product rule. And then when you took the derivative of each of these, it's a chain rule, and that's crazy. So we have something called logarithmic differentiation, using logs to make your life easier. So let's call this left side just y, just to make it easier on ourselves. We're going to ln both sides. And this is going to do for us amazing things. I'm going to rewrite square root as the 1/2 power. Okay, these are the rules we're about to use right up here. And this is, again, beautiful. If I'm taking the log of two things multiplied, I can separate as two logs being added. If I have the log of two things being divided, I can write as a log of two things being subtracted. So I'm going to take this one step at a time. One step at a time. The first thing I see, we have two things being divided. This top divided by that. So the law says I can write that as ln of the top minus ln of the bottom. That's a squared. Some of you are screaming at me, that's a squared, Yoshida. And you got me. All right, then we're going to use the other rule. Look, we have two things being multiplied. The property of logs says that I can separate that into the ln of the first one plus the ln of the second one. And then we have this. And it's becoming so much more beautiful. And then I have a property where it says I can p in from the log. I can p in from the log. So I'm going to apply that. This is getting better by the moment. Better and better and better. Now when I take the derivative, I don't have quotient rule, I don't have product rule, I don't have all that ugliness. I just take the derivative. Now realize what we're trying to find. We are trying to find dy dx. So understand, y is our function, x is our variable. Y is our function, x is our variable. So we need to take the derivative of both sides, but y is our function. So that's ln of box. What's the derivative of ln of box? It's 1 over box times derivative of box, but the derivative of y, by definition, is just dy dx. We got through that. 4 is a constant, and what's the derivative of ln of box? Well, we just did that. It's 1 over box times the derivative of box, but the derivative of the inside is just 3x squared. Let's keep going. Again, we have 1/2 as a constant. We just copy that. And we have ln of box. The derivative of ln of box is 1 over box times the derivative of box. So we need to multiply by the derivative of box, which is just 3. And we're almost done. Almost. I know the answer is going to be ugly, but if we had to do it with the quotient rule and product rule and chain rule, you would not have been a very happy camper. You would have like hated me for the rest of my life. So 1 over box, because we have ln of box, so it's 1 over box is the derivative times the derivative of box, but the derivative of that is just 2x. All right, let me simplify all this for you. 1 over y dy dx equals, I have 12x squared on top and x cubed minus 1 on the bottom, plus 3 on top and a 2 times 3x minus 1 on the bottom, minus 2x on top and x squared plus 4 on the bottom. We're almost done. Except what are we trying to find? We're trying to find dy dx. We don't want the 1 over y. So we should multiply both sides by y. Why? Because we want to get rid of it. Now, watch this. This is so cool. My life is going to be better because of this. I'm just going to copy and paste that. So I don't have to rewrite all that. Copy, paste. Uh-oh. There's some stuff I didn't want to come along with it, but it's okay. So I have a y, but what is y? I'm going to take my original y, all of that, and I'm going to copy and paste it again, because why do I want to memorize that? So I'm going to copy, and I'm going to replace this y, oh, I think I messed up, right here with, yeah, I messed up. I couldn't do that. I have to paste it before I do any of that. Copy that. Let me paste it here and explain what just happened. And let me explode that up a little bigger. And then I'll tell you what just happened. Okay. So I have this y. What is y? Y is our original function. So I have to replace y with all of that. So I just put that here. There is my ugly answer. That's it. Now, you may say that was a pain, but again, I would say to you, if you had to do quotient rule, whoa, that was bad. If you had to do quotient rule and then product rule and with all these chain rules, yeah, you would have been lost. Well, you may have been lost anyways, but you would have been lost. All right, that's the end of this video. Hopefully it wasn't too bad. Make sure you study these things because any of these things could appear on your quiz. All right, bye-bye.